So now it's my privilege and pleasure to introduce our first guest speaker this morning. So Dr. Rao will be joining us up here on stage. He is at Arizona State, and he's going to talk about artificial intelligence. We had a quick chat this morning, and he allowed me to share this conversation with all of you. I was letting him know that when I first saw a computer in person for the first time, 1979, several people in this room weren't born yet, I know, an Apple II showed up at my grade school. And the teacher said, I don't know what to do with this thing. Scott, you're like the social kid in the class. What are we going to do with it? What do you think the first thing I did with that Apple II was? Found a game to play, right? After that, it was like, we should probably do something useful with this. Me and a couple other kids figured out how to do some simple math on it. And I said to Dr. Rao this morning, I said, who knew back then that we'd be talking about artificial intelligence? And he reminded me that there was talk about artificial intelligence with computers way before that. When will computers think? We had a good conversation about that. One personal story, Dr. Rao, and then I'm going to have you come up, please. When we were chatting this morning, I asked him how he got into the field he's in teaching. He said, I always wanted to be a teacher. And he said, Scott, when I was a kid, remember when we were kids and they put us in groups and we all had to pick a profession? Everybody else wanted to be a doctor or a firefighter or a policeman. I wanted to be a teacher. And I was always the one who wanted to be the teacher. And Dr. Rao shared with me that his younger brother and sister are still have scars from when he was always teaching them when they were children. It's a great story. Dr. Rao, please join us. The time is yours, my friend.
Okay, wait, I need to get this. So you guys can hear me. Thanks for waking up early, and it's great to talk at Johnson Controls. I'm told that it was a company started by a professor. So professors actually can make companies that will stay for a very long time and have very big impacts, and that's beautiful to know. So I wanted to talk to you about the rise of artificial intelligence. I believe many of you have heard in all the news articles these days about artificial intelligence, and I want to sort of put that in a bit of a perspective and also talk about some of the challenges of making AI systems that will work with humans. Now, of course, I'm a professor, as I said, so we always start with a pop quiz. So this is the pop quiz. Explorer Magellan went around the world 3 times, okay? Are you paying attention? On one of those trips, he died. Okay, now you've done all this brain brew stuff, so think about which trip did he die in, okay? That's okay, so at least you can work on this while my talk is going on. The answer will be presented at the end. Okay. Okay, so as Scott mentioned, artificial intelligence as a discipline has been around from the very beginnings of computing. Many of you are probably aware of Alan Turing. I mean, I've heard of the name Alan Turing. You may have seen Imitation Game, which was about his life story. Alan Turing is seen as the father of computing. And I tell my students that when he invented the abstraction of Turing machine, which is, and also, of course, one of the first computers, the Enigma, the big thing that he asked is not what is the largest Excel spreadsheet a computer can handle, surprisingly. He asked the question, can machines think? Okay, this was a 1950 paper about can machines think. Now, I can't say that I've been thinking about AI from then onwards. I definitely wasn't born in 1950, even though I look old. But I was quite old. This is my bachelor's thesis from 1983. You can see beautifully hand-drawn pictures about speech recognition, automated speech recognition, and hand-drawn and typewritten pages. So I've been in this area for at least from then onwards. And now the interesting thing is that when I was in grad school, when I was working in artificial intelligence, mostly all that the rest of the world cared about artificial intelligence was why it can't be done. It's just not going to be possible. There's no way it's going to happen. So you see all these books in those days of Emperor's New Mind, or Mind Over Machine, or what computers still can't do. So it's as if the whole thing was, it's just not possible, so why are you wasting your time? So as a grad student, this was a great picker-upper that, lots of people, smart people are thinking that this is not going to go anywhere. Anyway, so I continued working, and I've been in the area for quite a while. And in fact, as time went on, essentially, I still had to, when somebody asked me, what do you do? What area do you work in? And I say AI. It was hard for them to figure out what AI was. In places like Wisconsin, probably they may even have thought of it as artificial insemination, which I believe was way more popular than AI in those days. Now, things have changed. Nowadays, actually, most of you have heard of the name artificial intelligence. I actually have a Google News thing that sends me the articles on AI that actually came out that day, and these are just 3 days worth of articles. Each column is 1 day's worth of articles, and you just notice that everybody is talking about AI. Clearly, why are you having me here? Partly because I think you probably are interested in figuring out what's all this hoopla about. And some of you are probably working in this area. Some of you are interested in figuring out what are the things that we can do with these technologies. Now, of course, this is another interesting slide that I saw, that the number of companies that mention AI in their earnings reports, okay, the thing that you all care about, from Q1 of 2008 to Q4 of 2016, and you notice that there has been a little increase in the number of companies that are mentioning AI. So it's as if you don't mention AI in your earnings reports, then Wall Street might punish you almost. So in fact, there is people in my area, we tend to think of this as maybe we are again in one more of these hype cycles. There's a large amount of technological progress that happened, but technological progress happens like this, and the perception goes like this, right? And of course, the same thing, the perception can fall down to. In fact, I think this time around, society at large is thinking about AI. So Obama, the previous president, essentially said, my successor will govern a country being transformed by artificial intelligence. This was less than 6 months back, when he gave an interview. So we are in an era where AI is sort of dominating the news. So what I want to do in this talk, because I had a harder time figuring out exactly the background of all the people, so I tried to sort of hit different levels of detail at different levels, so that every one of you will hopefully get something out of this. So I want to kind of give you the following answers to the following 4 complicated questions. You do notice that I walked on the Riverwalk yesterday evening, and I found this complicated question mark. Those of you who remember this on the Milwaukee River. So I want to kind of get us through why did AI get so hot right now? I've been working for 30 years, so it should have been hotter before. Why is it so hot right now? Why was the third time? And we'll talk about the fact that, in fact, one of the particular technologies that has been very useful in making AI this hot right now is this idea called deep learning, which turns out to be something an idea which has been tried many times before, called neural networks. And I want to bring up why is it that the third time wound up being a charm for the neural networks. I want to talk a little about are we done? So if in fact everything is working, as far as the technical progress is concerned, AI has reached its goals, and it's all just a question of doing some applications. And then finally, I want to talk about, won't somebody please think of the humans? How do you get machines and humans to work together? That last part actually connects to the work that we do in my lab about planning and decision making in the context of humans and machines working together. Okay, so that's the approximate agenda. So let me start with the first part. So why did AI get so hot right now? So let me start by showing you a block diagram that we show at the intro to AI, Introduction to Artificial Intelligence. The technical goal of the artificial intelligence as a field is to develop intelligent agents, which essentially sense the environment and will be able to act on the environment. And the whole question is, what do we do to increase our performance metric, which is some sort of a goal that the system has. And so you actually can see that the systems have to obviously keep track of, what is the world like now, what happens when I do a certain action, and what should I do next. So you're trying to figure out what to do next. So this is just the design of the agent itself. And then, of course, most of the AI as a field is in terms of figuring out how various of those black boxes actually get, how do we, come up with the formal foundations for them. Now, to get a sense of what might be involved in designing these kinds of intelligent agents, I find that it's useful oftentimes to think of the fact that intelligence, so an informal definition of AI is to make machines do things that when people do, we consider them intelligent behavior. Okay, so that's an informal definition. So the question, of course, is what is intelligence? And I'm not going to define it for you here, but we do realize that intelligence is multifaceted. It's useful to think of what human babies do when they start, learning to be smart. You see that kids typically tend to start showing very good perceptual intelligence. They start recognizing their moms and dads. They'll start basically vocalizing cute little sounds. They'll start putting everything in mouth. And in fact, they require to put everything in mouth. They have to do very complicated maneuvering, and they learn all that somehow. They learn some emotional intelligence, and they learn some social intelligence. And only much later, when your bank balance is high enough that you can pay them tuition, they can start going to schools and start getting these cognitive intelligence aspects, SATs, and going to universities and getting the degrees. So that's sort of, at least those are the different facets of intelligence. It'll be, and then it's also useful to sort of know informally that human babies seem to be getting them from the top to the bottom, perceptual to emotional to social to cognitive reasoning tasks. The reason I bring this up is it's kind of interesting how AI systems try to show the different kinds of intelligence. So historically, the last time AI was very much in news was in 1980s. I don't know, some of you may have been around. At that time, there was this huge big thing called the expert systems revolution, where essentially every company would sort of look at its processes, write it in a sort of a rule-based format so that then you can, essentially the system can do diagnosis, do suggestions as to what to do next, and so on. So that expert systems was like a big breakthrough in 1980s. And then, of course, after that, in 1990s, it's actually exactly 25 years this year. In 97, Deep Blue ended the human dominance of chess. For whatever reason, we somehow decided chess is a hallmark of intelligence. Being a very bad chess player, I think that's actually silly, but we decided that chess is the hallmark of intelligence, and Deep Blue dethroned Kasparov in 97. So he was the first human being, as he says, to lose his job to a machine. So, and in fact, he wrote a nice editorial op-ed in Wall Street Journal last week. You should really read that. It's a very nicely written article. And in fact, that editorial is interesting because there's a significant worries in people's minds as to do we all lose jobs. And as the first guy to have lost job, he gave like some words of wisdom to the rest of us who might be. Now, in 2006 onwards, in fact, until the most recent times, the big improvements in AI technology have been in perceptual tasks. The ability to see things, ability to understand speech, not understand, basically recognize speech, the stuff that I was doing back when I was an undergrad. Now, of course, all of you have it on your cell phones, right? It's not my technology, but essentially speech recognition itself is, we take it for granted right now. Image recognition has improved, speech recognition has improved, natural language understanding is been improving quite significantly. And of course, that's the way the improvements in AI have come across. Now, if you go back to the different intelligences and the way people develop, the human babies develop those intelligences, if you are following me, you might have seen that it's kind of interesting that while human babies seem to be going from perceptual towards cognitive, AI systems started cognitive and only now became better at perceptual. So it's almost reverse direction in terms of the way the progress has happened. Now, if you understand that, actually, it explains a lot about what's going on in AI right now in terms of public perception of AI. The directionality actually winds up being understandable as to why the progress had to be from cognitive to perceptual rather than vice versa for the humans, and why that made AI a household name right now when it wasn't before. For the first part, essentially, we tended to start programming computers with theories of tasks for which we have theories. We have theories of how we play chess. We have theories to some extent of how we play Go. We have theories of cognition. We don't have actually theories of how we see the world. People tried, but in fact, mostly we seem to have learned to get speech and natural language and vision essentially without understanding. That's sort of subconscious. So for those, if we made up theories to write it to the computers, they were mostly made up, okay? And so most of the time, essentially, computer vision as a field or speech as a field had tried to come up with theories that didn't work as well, and they had to wait until the systems can do what we did, which is just learn from massive amounts of data. You know, it's hard for you to believe this right now, but when we were kids, and if you had kids, you see that most of the time they don't do anything. They just be very cute and essentially soak up information. Okay, if the robots can be cute and soak up information, you know, if they take like 20 years before they start bringing in any money, we get really mad at robots. But apparently, we like this when our kids do it, right? So in some sense, a lot of learning happens where because we don't have actual direct theories of it. It's actually important to understand that the world we live in, part of it, we just learn the theories from the data. That's important. But there's also doctrine. You know, you don't get employees into Johnson Controls and say, just hang around for about 20 years, figure out what we are doing, and learn from that how Johnson Controls works. If you do, you wouldn't be around by now, right? So in essence, there is both the data and the doctrine, and we had to consider which parts had to be used for what sort of intelligence tasks. And so that's one aspect. The second, why did AI catch public imagination right now? Well, that's because essentially early AI of the kind that, in fact, when Deep Blue won against Kasparov, it could not actually recognize a chess piece if it came and beat it. It had no sense of actually vision or our speech or language, but it's all pure brains, what we call pure brains. It could do chess game moves, multiply down. Okay, so as I say, essentially the early AI was a blind and deaf Socrates. Okay, and it's hard to fall in love with Socrates. You know, if you have a kid who just basically doesn't say cute things and is in their head doing humongous calculations, those kids probably won't be loved as much. Not surprisingly, AI was not loved as much before, whereas now all of you have AI technology on your cell phones, and you're talking to them, and mostly they're just doing these perceptual tasks. All of a sudden, when the perceptual tasks are happening, we now see AI everywhere, and also that leads to a lot more misconceptions in the public about what AI can do, based on what it's doing currently. So it's sort of useful to have that in the background to have a sense of, it just didn't happen last year. It didn't, even though if you look at the public media, it looks as if just the whole thing happened last year. It's just what certain aspects of intelligent behavior, we figured out how to automate them through learning techniques more recently. Now, I said learning, and then so I want to talk about, I'm sure many of you who heard about AI probably also heard about the buzzword deep learning. And so that's why elephant in the room, and we need to kind of talk about a little about what deep learning is, so that next time when you are in a party conversation, I guess AI people, basically party conversations will be about deep learning. And so you can too take part in it and sort of impress your friends about More importantly, of course, you can have a sense of what the technology is useful for and what it's not. So deep learning is really responsible for some of the successes recently in perception. But it turns out that it's just a rebranding of a very old idea that's been around for quite a while, called neural networks and training of the multi-layer neural networks. For those of you who may not have heard of this technology, neural networks, it's here a one-slide summary of what happens in neural networks. It's sort of loosely based on our theories of what human brain might be doing. In fact, human brain, the way it works, is a complete open problem, mostly. In fact, as somebody said, if understanding human brain is a 1 mile long trek, we have currently walked 3 inches of the 1 mile long trek. So that's where we are in neuroscience. But despite that, we at least know that brain has neurons and neurons are connected to each other. So for quite a while, people tried from back in 60s onwards, people tried talking about connecting very simple computational units, where these computational units, for example, the one in the middle, it's essentially getting inputs, some real numbers as inputs, and they're multiplied by the weights on the connections, and then they're summed up, and then a nonlinear function is applied to it. Typically, that nonlinear function is a thresholding function like the one that I showed there. And if this input is over, the summed up input is over a threshold, then the neuron, the unit fires, and then its output is then connected to somebody else's input. So this is the basic idea. So a very simple form of neural network, what's called a feed-forward network, where all the information just goes in the forward direction, is essentially shown on the top. So you start from the input layer, you are connecting it to one hidden layer, another hidden layer, and then finally an output layer. Now, the reason neural networks are interesting is it turns out that essentially, as long as you have a nonlinear function being used to threshold, there's a theorem that shows that a network which has just one hidden layer, can approximate any arbitrary function. Now, this looks too much like a magic, and it is. The reality is that given any arbitrary function, in the whole wide world of single hidden layer networks, there exists one. There are infinite number of those, okay? There exists one which would be a close approximation to your function. Finding what that is trying to figure out how many units are in this middle layer and what are all the weights connecting these units to other units. And that's supposed to happen essentially by function optimization, continuous function optimization. And those of you who obviously know calculus realize that you could think of this function optimization as essentially some form of a gradient descent, and the gradient descent steps are done using what's called back propagation, which itself winds up being just a fancy name for chain rule of differentiation that you definitely remember and your kids in high school know. Okay? So you basically just do chain rule of differentiation to sort of slightly change the weights based on what's predicted and what is supposed to be true. So you propagate the error back into the weights. And over a period of time, you're guaranteed asymptotically to find a local minimum in the space of these networks, and that might oftentimes be good enough. So that's just the background on what a neural network does. Now, so what about deep learning? Deep learning is essentially neural networks. It's just been rebranded. First, back in 1960s, Frank Rosenblatt essentially invented this idea and tried to do it, and he was actually very happy about the fact that he could do single layer networks, no hidden layers whatsoever. And of course, there are some theoretical limitations. At least, unless you have at least one hidden layer, you don't actually have the ability to approximate every possible function. It turns out perceptrons can only approximate linear functions, which is only a subset of all the functions you can approximate. In second coming, back in around 80s, they figured out how to actually train networks that have hidden layers, and using this idea of backpropagation. They invented it as backpropagation, but really it's just chain rule. And that idea itself, the fact that it works, was first realized back in '69 by a control theory people, Bryson and Ho, and then again got reinvented in the 1980s by Rumelhart and Hinton and so on. And there was a humongous amount of enthusiasm at that time. And for a while back in 80s, again, neural networks were all over the place. Everybody would try to apply neural networks for their favorite problem. The problem, of course, was the learning was extremely slow. While it is possible to do it, it takes forever to train these networks. I remember we tried to train like a 3-layer network, and my grad student would essentially start the training and go off on a vacation and come back after a week. And if the computer hasn't crashed in the meantime, it might have found some reasonable local minimum. So that was part of the reason why it wasn't going too far. Now, of course, more recently, things have become obviously doable, and that's why we are hearing about it. So the question is, why is the third time such a big charm? And it turns out this is sort of a useful thing to understand, that there are like 2 types of reasons. One, of course, between 80s and around 2012, there have been some theoretical advances. And there's been also, the world changed during that time. Not just AI, but the rest of the world changed. How many of you have seen Blade Runner, the movie? Okay, I request you to, it's one of the greatest movies. If you have seen Blade Runner, then you see everything else like Matrix, etc., as just derivative stuff, right? Now, the interesting thing is you go back and see Blade Runner now, and you'll notice that while they were thinking about like ultra, what happens in way, way late in the future about how robots and humans can become indistinguishable, their TVs still were huge, big TVs. They never thought of the possibility that TVs can be LCD TVs. Their phones would be huge, big boxes. They didn't think of iPhones. Okay, so while you might be able to kind of project what happens in the future in one dimension, every other dimension is changing too. And one of the big things that changed in AI is, while of course AI people are figuring out how to improve neural networks, the rest of the technology, the rest of our society changed. That basically goes back to that second column, that advances in essentially computing infrastructure, and way more importantly, advances in our ability to capture data. That wound up becoming very useful. Let me go through both of them very quickly. On the theoretical advances side, people have figured out, for example, that for very deep networks with many, many neural units, one of the biggest problems is these are very high dimensional spaces, and figuring out a good place to start helps you to at least find the local minimum. And otherwise, one of the things that would happen is all weights will, after some number of iterations, all weights will become 0, and then you'll just stay in 0. Okay? People have figured out some nice initialization techniques. In fact, one of the cute ones is Xavier initialization. One of the other things they found, again, is while any possible nonlinear function can be used, it's important to make sure that the function that you're using has derivatives that don't vanish. Okay? And it turns out the one that I showed you, the normal threshold function that I showed you, even from the elementary calculus background, you realize that gradient is 0 here, gradient is 0 here, and gradient is non-zero only in that very narrow region. And so the question is, you want to have situations, function forms where the gradient doesn't become 0. And these rectified linear units, which sort of go like that as a line, will essentially have that property. That's one of the small advances that wound up being important. And finally, for any machine learning technique, the biggest problem is this notion of overfitting. Essentially, instead of learning to predict patterns, you just memorize the data. That's what overfitting is. And you want to avoid the overfitting, and it turns out actually in machine learning that this idea of Bayesian learning actually is the cure-all for it. It's just too hard to do it. And it turns out there is an idea called dropout in neural networks that helps you get to that point quite reasonably. Okay, those are the theoretical advances. On the data computing infrastructure side, as I said, people start talking about we are producing data as if for most of our life, before computers were invented, apparently humans were not producing data. They were not breathing, they were not talking to each other, they were not thinking. It's not, obviously that's all made up. We were producing data all the time. It was just going into this free space and it was falling off. Whereas right now, anything that happens, United airlines was producing data by dragging passengers all the time. It is now caught on your cell phone. And so everybody gets to see it. Do you see what I'm saying? So the whole point is that the data is being captured left and right. And because of which, once the data is available, you can then use that to train these networks. And it turns out that the amount of data that is used to train that networks has increased significantly. And that was like a big reason why neural networks have become more usable. And of course, while Jensen Huang would like to let me tell you that really NVIDIA is just as important, that the GPUs are as important, it's somewhat important, but really the data ability, the fact that we can capture much larger amounts of data wound up being very important. Now, if these two columns are both increasing, have led to the ability of multi-layer neural network training by 10,000-fold, which is at least back 2-3 years back, it's 10,000-fold. It's now increased even more. An interesting question would be how much of the 10,000-fold is because of the theory, how much of the 10,000-fold is because the rest of the world just caught up. Now, as an AI professor, I would like to hope that this is essentially 10,000 for the theory and 1 for the data, right? Unfortunately, 100x from the theory side and about 1,000x from the rest of the world catching up. Okay, that really wound up being important. So these are the technologies just waiting in the wings, and then the rest of the dimensions, we started making progress in terms of capturing the data and having this utility computing, and that suddenly made things start ticking. Okay, that's worthwhile remembering because people are likely to tell you that things have somehow gotten done newly, but that's not necessarily the case. Now, just to give you an idea of how much data capture made a difference, in the whole field of image processing for the longest time was obsessed with that picture. Okay, they were not being sexist. They needed a picture and that they could try it out with, they could try out their ideas with. And this is the picture of Lena, who happens to be a Playboy model. But they took that particular picture and they would do all sorts of, the edge detection, et cetera, on that. So much so that at one point of time, the top image processing conference in the field requested her to come and be an invited speaker in the conference, because she was like the reason for this system, for this entire area to exist. Now, that's sort of one picture. Mostly, we'll see these pictures in the image processing papers. And now, of course, back in 2012 timeframe, they started having this, essentially when web and iPhones have started capturing pictures everywhere, and they essentially started having this ImageNet, which was about, it's useful to know that ImageNet, when it started, it was about 100,000 photographs culled from the web, and then they were manually categorized, a whole bunch of them were manually categorized into 1,000 classes. And by the way, it's useful to know a little about ImageNet because all the techniques in computer vision for neural networks are based on ImageNet. And so in some sense, they learn whatever is in the ImageNet to some extent. And of the 1,000 classes in the ImageNet, 200 of them are dogs. Okay, this is very important to understand. So when we dream of people. Tend to, maybe unless some of you dog lovers might be dreaming of dogs, but neural networks, when they dream, they can easily dream of dogs because they're mostly being trained on ImageNet data where 1/5 of the classes are different kinds of dog breeds. Okay, it's useful to know because this is what you train on is the patterns you will wind up learning. So you should actually see this thing called Deep Dream on the web, which is essentially neural networks which try to start hallucinating. Given a picture, they start hallucinating to see patterns in it. And it turns out that just as we tend to see human forms, Mother Mary in a slice of toasted bread, right? Neural networks see dogs pretty much anywhere. The moment they see dogs, you can make them see more and more dogs. And so you can see these beautiful cloud pictures with dogs flying everywhere. Okay, it's useful to know because data makes a difference in terms of what you learn. Anyway, so that's ImageNet, and much of all the computer vision progress is connected to how the images on the ImageNet have been actually, they've been classifying those. Okay, of course, currently ImageNet is much bigger. It's about 14 million images, and One of the particular type of neural networks called convolutional nets have been used to essentially play with these ImageNet images. And they are similar to the feed-forward networks, except they are slightly specialized to take into account the fact that images have a particular kind of this grid-like structure. So essentially, they will do the filtering, take a small region and multiply the numbers there with the filter coefficients, and then take that and feed it to a pooling layer, and then essentially each of these intermediate layers are sort of learning internal patterns of the images. The difference is that these filter numbers are themselves learned through the backpropagation, which is the same machine learning algorithm. Okay, in terms of the actual state of the art, the deepening war in convolutional nets is that they found that the deeper the network, the more patterns it can actually find. At least in terms of the ImageNet competition, back in 2012, there was an 8-layer network. By 2014, there was a 24-layer network. By 2015, Microsoft, which is close to currently the state of the art, as a 150-layer network. And it has about 5% error on the ImageNet images. That means when you show an arbitrary image, it will say what are the top 5 classes out of those 1,000 classes. And if the right class for that image happens to be in one of those 5, then you get a point. Now, it turns out that humans have a 5.1% error. Apparently, we don't know how to distinguish every possible kind of dog anywhere near as well as neural networks can do. So before you give up on the human ability to do anything with respect to images, let me just point out also that while most of the work on image in the deep learning and neural networks has been essentially on perceptual tasks, as I pointed out, vision, and part of the reason for that is for all these tasks, the input is quite clear. There is a very natural form of input. For images, everything that can be talked about an image is in the pixels of the image. For the speech, it's in the speech signal. There is nothing more than is in the speech signal. And for the natural language, it will be the text. So the inputs are clear. Now, in most other tasks, input features oftentimes still have to be hand-coded. And I want to bring this up because for you guys, in addition to just finding if there is a fire going on in a building's picture, which you can do using existing image-based neural networks, you might be, for example, interested in this work that some of you probably heard of last year, where Google got a lot of press for it. In fact, these days, anything Google does with deep nets gets a lot of press, which is this Google data center optimization. And there, essentially, what they had to do was they were just basically looking at the power usage effectiveness of their data centers, and the network they trained had just 5 hidden layers. Connect that 5 hidden layer number to the 150 hidden layers for the image recognition network. It's a much smaller network. It didn't really need to be anywhere near as big as the other one. Part of the reason for that is they had to start with hand-selected features because it's not completely clear what is the natural input to the network if you're trying to optimize power usage effectiveness. So in fact, what they did was they came up with those 19 features. So Johnson Controls can actually look at it. Some smart engineers can look at it and say, oh, they're actually missing some very important features. We have to throw that into the mix. And you throw more of the features into the mix. One of the advantages is you can throw all sorts of irrelevant features, and the network can figure out if it is relevant or not. It's a kind of a useful thing to keep in mind. So are we done? Now, probably not yet. So it turns out that there is an irrational exuberance around this whole technology of neural networks. I think of this an apocryphal story that when Archimedes found the principle of lever, he said, give me a long enough lever and a place to stand, I will lift the universe. Okay, and the variation of that in the neural network era is give me a big enough GPU, a large enough data set, and a deep enough network, I'll create you super intelligence. Okay, obviously, I would love to believe that is the case, but it's not really because there are many big problems that we haven't yet solved. And this kind of irrational exuberance happened in AI before too. At the time of expert systems, instead of a GPU for every computer, it was a list machine for every desk. Okay, and so there was that sort of an issue there too. In fact, people have gotten so drunk with this that there was this paper recently last year which said automated inference of criminality using face images. Okay, so this is phrenology back in circulation again. So somebody looked at this data is being captured everywhere. So you get the pictures, mugshots of all sorts of people, and then see these are the people who have been convicted. These are the people who haven't yet been convicted. And so, and then basically train your network with a large layer network using the same image recognition software. And this paper basically points out that CNN, which is not the fake news network, but rather the convolutional neural nets. That's one other way you know that you are an AI guy. When you hear the word CNN, you don't think of the news network. So CNNs are getting 95% accuracy when shown an image, they're able to say with confidence, oh, this person actually, this mugshot belongs to a criminal. So we can actually stop having all these Supreme Court judge confirmations. We don't need court systems because CNNs can do this, right? Of course, this has got us a lot of notoriety. There's a huge amount of news articles basically worried about the ethics of doing these kinds of things. Okay. In fact, somebody said this paper is the exact reason why we need to think about ethics in AI. But leaving ethics, which itself is a very big area, I would also want to ask you, do we really know that just because the system works on some examples, do we really know that it's working on all the other examples for the same reasons we expect it to work? And to put that in perspective, let's just notice that in this case, so on the left-hand side, you have a school bus, and then I add some piece of this middle noise to get the right-hand side image, which most of you probably can't tell the difference one bit. They both look exactly same. Most existing top quality neural networks, pre-trained neural networks, would say the left-hand side one is the school bus, the right-hand side one is an ostrich. Okay? Now then you take a dog and you add some noise, the right-hand side one looks still like a dog to you because you're just human, you don't understand the difference. Turns out it too is an ostrich. Okay, now of course it's possible that that the world is more full of ostriches than you know, but the reality is that when the system works, just because it actually got the classification right doesn't necessarily mean that that it's looking at the world the same way you are looking at that world. So I use this word called sphyxiousness, which there's this long story about Sphex the bug. I won't go into it, but the basic point is that when we see somebody show certain behaviors, we then put an example closure around them. So if somebody does differentiation, you think, yeah, they should know how to do addition and subtraction and multiplication. This is based on our understanding of how humans work. But I can give you a machine which can do differentiation, which probably doesn't know the notion of addition and subtraction and multiplication. This example closure winds up being very important when these systems are put in the middle of human societies. And that's worthwhile to understand. Another way is we tend to think in our mind that there should be in some space, these classes are nicely put into some contiguous regions. But what might be happening essentially is only certain small slivers of a high dimensional space, the system knows what the class is, and rest of everywhere, it basically is completely lost, and it's just tossing a high dimensional coin. Okay? That's part of what is happening. So I want to just sort of quickly go through the thresholds left, and then obviously see if there's any time for questions. So common sense is one thing that brings back our Magellan guy. AI systems still miss common sense. By the time kids understand certain things, they've already got a whole bunch of common sense when they're age 6. So the systems that we have still don't have common sense, and that's a big threshold we have to cross. In addition to the trip in which Magellan died, which I hope you have realized is trip number 1, Vinograd schema challenge is another cute example to keep in mind, where there are these two sentences. and both of them have the same pronoun, but the pronoun refers to something different. Okay, and you guys realized it, I hope. Okay, the women stopped taking pills because they were pregnant. What they? They, the women, they, the pills. Okay, and the women stopped taking pills because they were carcinogenic. Which is they? They, the women, they, the pills. You know which is the which in both these sentences. The sentences are exactly the same, and you get it. How do you expect the machine will get it without having the common sense about a whole bunch of things that you are bringing to bear? So in fact, Vinograd schema challenge is currently like a challenge task that AI systems are subjected to. One other big issue is models. We talked about models in I think, at least in the brain brew competition, somebody was talking about model predictive control. We used to be interested in providing models to the machines, and then they'll start reasoning with them. One problem, of course, is the models are always incomplete, and you can do a lot more destruction with ignorance than without any malice, even if you're worried about all these superintelligence worries. And in fact, this Don Rumsfeld once said that we have known knowns, known unknowns, and unknown unknowns. And while Don Rumsfeld is probably the the wrong person to follow the philosophical advice on, actually it turns out that's a very important thing for AI models to work on. How do we deal with known unknowns and unknown unknowns? In my own group, we actually look at that in a significant way. We talk about planning models that wind up having these different levels of incompleteness and how to handle them. I have almost run out of time. Can I say how many minutes I can take?
Take as much. Yeah, take as much as I can.
Never say that to a professor. Okay, so then the next thing I want to talk about is, won't please somebody think of humans? Okay, I wanted to bring that up because, in fact, that's also close to my heart. I happen to be a human, and I want not to be removed from my usefulness in the society. So AI has a curious ambivalence towards humans. Okay, we seem to be, our systems, AI systems seem to be happiest either far, far away from humans, such as Spirit and Rover on Mars. That's AI technology completely in operation. Or when we crush them. We crushed the human dominance of chess in '97, human dominance of Go in last year, and human dominance of poker this year. And we seem to be very happy about these. And yet we want society not to be too worried that AI is going to take over the world. How exactly do you expect this to happen, right? So why don't we want to work on systems that know how to work with humans in the loop? And so last year, when I was the program chair for the International Joint Conference on AI, which happens to be one of the main conferences in this area, I decided that the special theme for this would be, the conference going to be human-aware artificial intelligence, with the tagline that why intentionally design a dystopian future and spend time being all paranoid about it. So you should start working on humans in the loop from the beginning. Now, one of the big issues is if you put humans with the machines, isn't that cheating? Okay, and it's not a worry, not a surprising worry. In fact, in the beginnings, early history of AI was full of humans actually cheating by providing the machines the knowledge they needed. Okay, you all know MTurk, mechanical Turk, that Amazon has. The original mechanical Turk is that guy, that Turk. Okay, who would be able to answer questions and would go from one European kingdom to another European kingdom, impressing kings and getting lots of money. And it turns out that if you open it, there's a little Turk actually sitting there, who is the guy who's answering the questions. Okay, so there is this worry that if you put humans in the loop, maybe they're just basically, it's the human who is showing the intelligence, not the machine. That ship has sailed long back, honestly. Okay, really what we want is that by having humans in the loop, AI systems, the scope of AI expands significantly, and I want to show you that there are some very interesting research problems that we have to deal with once humans are in the loop. And it also reduces some of the off-the-top worries about AI and brings up, as I said, novel research challenges. My classic point about this is this guy, poor guy running away from the tigers, is that we needed the brains we have not to run away from the tigers of the savannah, but to deal with each other. This is an evolutionary fact. We didn't need this ridiculously large brain, okay? And so reasoning with other humans, other agents, and reasoning about their mental models winds up being mostly what we use our intelligence for. And AI systems don't do that right now. Remember these many facets of intelligence I showed you? It turns out the emotional and social intelligence are the Rodney Dangerfield of AI. Come on, guys, somebody is old enough to remember Rodney Dangerfield, right? So they didn't get any respect because that's the non-engineers. Of course, some engineers doing AI probably was part of the reason, because in my class, when I show this slide, I say, those of you who are men, apparently you are the ones missing the emotional intelligence. And those of you who are engineers, apparently you are the one that are missing the social intelligence. And that typically takes care of 99% of my class. But the point is, if you want the systems to work with you, they need to have emotional and social intelligence. And engineering part of our brain always said, that's all touchy-feely, we shouldn't be interested in it. But it turns out it's very important, otherwise you're not going to work with these systems. You throw away a system because it interrupts you in the wrong time. You throw away a system because if you remember the Microsoft paperclip, the reason people hated it was because it had this really big smug smile. And it shows up exactly when you are feeling extremely frustrated. Do you want people to have a smug smile when you're frustrated? That's a simple thing. Engineers think, yeah, that's not important stuff, but hey, that's the reason why it went out, right? So if you think about, even from a theory point of view, remember I showed this picture way back when we started. This is the architecture of intelligent agent. Now, it turns out that the intelligent agent with the human in the loop suddenly becomes significantly more complicated, because now it's not just maintaining the environment state, it's maintaining the state, the mental state of the human in the loop. And if you have lots of people, you're maintaining the mental states of those lots of people. And that's actually quite taxing. We do realize that part of the difference between normal versus autistic behavior spectrum is that people with autism have difficulty modeling the mental models of other people. So in some sense, AI systems right now are on that level. And so we want to work on how to get them to have these human-aware facets. And in my own lab, the last few slides I want to show you is we work on these challenges on human-aware AI, in particular human-aware planning and decision-making. We talk about how to, some of the challenges we work on are how to interpret what humans are doing based on incomplete human and domain models, how to plan with incomplete domain models, talking about robustness and so on, how to show explicable behavior. One of the things that you want is if you have a robot working with you, if it does something that is optimal for it, but it spooks the heck out of you. Imagine a Baxter, the huge big Baxter, trying to help you by flicking off some dust from your nose. You will never again use that robot, right? Because you're basically spooked by it, and so it needs to understand what is optimal versus what is expected of you, and do that, okay? And then finally, a bunch of engineers deciding what humans want is a bit of an oxymoron. Really, you need to work with human factors people to make sure that these systems are actually, from the beginning, from the get-go, have taken these pieces into consideration. So I'll just show you 3 videos before ending about my own lab's work. So for intention recognition, this is some work that's going on right now, where we are using the robot is able to, in addition to actually just language, is just able to look at what the human is thinking through essentially a brain-computer interface. We just got this emotive helmet, which sort of tracks some of the brain waves, and it doesn't completely read your brain by no means, but it is enough to tell what the human is looking for, what block they want to use, so that a fetch robot can pick the other block. And you'll notice in those cases that when this thing happens, this guy actually becomes very happy, and the other guys were worried because it wasn't doing what he's expecting it to do. Okay, so that's one of the kinds of work that we do. I just want to see if he would. There's a bit here where the guy in the middle becomes very happy that the robot actually figured out what he did, what he was thinking. But we'll pass that. Intention projection, the robot doesn't necessarily have to talk to you. We now have, once again, we have this technology developing, just like we have brain-computer interfaces, we have HoloLens, which basically you are seeing the world, and the world is being augmented with the reality. The reality is being augmented with additional projected information. So in this particular case, the robot is projecting into the human's visual field some information about what blocks it wants to pick, what blocks it wants the human to, is leaving for the human. And that allows, again, for additional more fluid collaboration between them. So the HoloLens for projecting the intentions, and the brain-computer interfaces for recognizing the intentions. Of course, you can do it by talking too, but actually we too say that a team works extremely well, then it's almost wordless communication because they've gotten used to each other so well. And so that's one way it can happen. And theoretically, what is the big difference in these cases is you realize that the machine and the human have very different models of the world, and providing explanations winds up trying to reconcile these models. What is expected of me versus what is optimal for me. This is my last slide, which basically shows that you can actually, in this case, the robot might be trying to transfer some hot liquid as well as a costly iPhone from one table to another. The optimal thing is to put both of them on the same tray and walk down, but it might actually spill them. But it turns out that what the human is hoping for, because of their worries about its capabilities, are that it will take them in 2 trips with 2 different basically trays, and that winds up being a more explicable thing as far as the human is concerned. That's something that gets done automatically. I'll skip over that. We work with human factors people to actually set up human machine studies where we actually make sure that these theories hold up. And then, of course, the whole thing here is being used in the context of a plug-and-play architecture for multi-robot system where multiple robots can plug in and plug out. So here there are like 2 robots, and there are some humans involved and some tasks to be done. And as the robots plug out, then the tasks are distributed to whoever is left. And I'm going to end. So to summarize, essentially, I wanted to talk about a few things. Why did AI get so hot right now? And I think that's because the progress in perceptual intelligence wound up making it possible for people to enjoy the fruits of the AI technology. Why is the third time a charm for neural nets? It's not really as much about just the AI technology itself, but it's because other things like our ability to capture data and the utility computing have become possible. Are we done yet? Not anywhere near close. We still are far away from things like common sense, incomplete models, ability to work with humans, but it's an amazing technology. And it can be used quite carefully. As long as you understand its limitations, it can be used for lots of things. And then won't somebody please think of the humans, modeling the humans in the loop, recognizing their intentions, showing explicable behavior, and providing explanations. These all wind up being important. These are actually capturing these touchy-feely emotional and social intelligence aspects. Thank you for your time, and I'm going to stop here.